to the talk by Andronick Arutyunov about derivations in models over group algebras. Значит, это вы куда-нибудь в карманы. А это, значит, можно на голову, а можно просто нацепить, главное, чтобы вот этот клокочек был недалеко.
Так, это как? Вот так вот?
Ну, например, так, я думаю.
Так
что,
нормально будет?
Я думаю, что
Научно.
Ну, можно как-то воротник купить.
Попробуем. If you hear me, then I will start. I'm sorry, I have got some problems with my voice, but I believe that I will have a talk in full size. So what I'm going to talk about, if we have got group algebra, today always G is in most of times infinite, but finitely generated group. So G has got a finite set of generators, and group algebra, or it would be more precisely to say a group ring, it's such linear combinations. Alpha is a complex number, G are group elements, and we will talk. My purpose is to talk about bimodules, Banach bimodules over this group ring. Bimodule, I mean the following: I have got some norm function in this one. They're finite.
Infinite, I understand. This may not be, maybe uncountable.
Sorry, the group.
No, there's some maybe.
I understand. Group is I'm sorry. Sum is finite. So almost all alphas are zero in group ring, and in Banach bimodule, no. Banach, I will talk about such bimodules when you have got a norma on a group ring and you have got a closure under this norma. So that's our bimodules about which I will talk about. For group rings, in most of literature, they say that a group ring, then sums are finite. And when we're talking about group algebra, so there are different readings. But if ring, then this sum must be finite. Of course, sure, you can have a lot of elements, but finite. So what is the derivation? The main question, what we are going to talk about. Derivation is a linear operator from a group ring to, we will denote this bimodule A, to the bimodule A, such that it's, first of all, it's linear, it is bounded as an operator, and the Leibniz rule holds. So everybody knows this rule. We don't have nothing from super mathematics, no, just common Leibniz rule.
Yes.
Leibniz rule, yes.
Leibniz.
Yeah, very Leibniz. So as it is, as we teach students on first course of calculus, just common Leibniz rule without any without anything. So my purpose is to understand how these derivations look like in such bimodule. Of course, I cannot give you a theorem for all bimodules, but I can say I will prove the theorem that
there's a norm, right?
This is norm, yes.
He doesn't have any, doesn't depend on the norm. So
It depends because it must be bounded. It must be bounded. What I'm going to prove that all derivations in, for example, LP of G are quasi. Oh, I will write it quasi inner. What means LP? I will define a little bit later, but you understand what is this. You must, this coefficients must be from LP space. Nothing difficult. And what means quasi-inner? Quasi-innerity means that such derivation can be written as a formal sum of inner derivation. What is the inner derivation? Inner derivation is a derivation of the following view. Just a moment, sorry.
only finite in power.
Only?
They're only finite in power.
No, in LP, of course, they're infinite. Here, yes, but the image of an element from here can have infinitely many elements, of course. And sure, if it is bounded, then you can then you can continue this operator to the operator which acts here, but it's not important for us right now. I give the definition of the derivation in more simple view. It's easy to work with it in such a view. And of course, we understand if it is bounded and the Leibniz rule holds, then you can continue it. Then the Leibniz rule will also hold, but you have to understand what means this, because this is an element of bimodule, and this is an element of bimodule. So you cannot multiply them because it's a bimodule just over the ring. So we have got some problems there, but it's not interesting for us to solve that problem. So we will talk in the most easy way. So what is an inner derivation? Inner derivation is a derivation of such a view. But of course, here, A must be from A. So what means quasi-innerity? I will explain it again a little bit later when we will see that it is natural type of derivations. But informally, right now, it means that this, in quasi-inner derivation, this element can be not from A. It must be from some formal space which is bigger than A. And innerity means that this commutator, I remind what that means, it's A minus AX, that this commutator is with the element of from A. So, yes.
Yes, but
Bimodule, yes. Why bimodule? Yes, because here I take here UV from group algebra. When I map by D on U, this element is from bimodule, not from a group ring. Perhaps you have to multiply it on the right side, and here you also have an element from bimodule, and you have to multiply it on the left side. Then you.
in your notation, A is just the closure of the group.
A group algebra, yes.
Yes, and so you consider derivations from the group algebra to its closure, or to a more general logic, to some bimodule or or you consider only these derivations?
Yes, I consider just such derivations, only this. About other types of derivations, I will say several words, but later. So, and it's very important for us to understand what is the norma, how looks the closure like. This will be a little bit later. So, the main theorem which I will prove that derivation in LP from G, group LG, bimodule over, yes.
So you consider closure. What is topology of?
No, topology is generated by norma. It's a normed space, but it's a Banach space, so you have got a topology from the norma.
Just some norm. No.
Now, yes, some norma.
At the moment, just
At the moment, just some norma. In the proof, in the theorem, I say that not all normas, but for LP norma. But a little bit later, I will explain which normas we can check and so on. So we will return to this. So main idea, our main goal is to prove that all derivations are quasi-inner. But what is quasi-inner, I will define more precisely a little bit later. Now, I have told what about the speak will be, and the main very question which is asked usually, why I'm interested in such derivations. Well, there are different purposes to study some derivations. I will mention two of them. First, I have found that some colleagues, for example, Reedon, Haggis, and others, they found that such derivations are useful for Reed-Solomon codes. Reed-Solomon-like codes, Reed-Solomon coding. I don't understand precisely why they need them, but they have got several papers where they say that if you have got a derivation, then you have got a code, so you can prove something. Coding theory is not my area, so I just say that it's good guys. Inner derivations, yes. Inner derivations are already not, but perhaps we have got others. So that's another colleagues, for example, Johnson, Barry Johnson, Sakai, and Polanski, and a lot of others. They had, for example, such hypothesis that if you take this kind of algebra, then all derivations here are inner. Well, they will look like that. Why they needed to study derivations? Because there are big connectors with higher measures and other questions of analysis which are about that. So in fact, the derivation problem, also known as the Johnson's problem, the derivation problem, is the following. All derivations in L1, in big L1, are inner. Note that here,
you said that last word.
all derivations are inner.
Are all this.
This is a hypothesis. It was, I think it was proved by Victor Lozert. I'm not sure because that it was proved because he proves that all derivations in other case are inner. Then he says that everybody knows that from that follows this this statement. I'm not everybody. I don't understand why it follows, but it was published in Annals of Mathematics. So I think that if it is written in Annals of Mathematics, then it's true. It's my promise that I don't understand why. First of all, secondary. My purpose to why I am interested, because I think that we can have a calculation of pseudo-differential operators in group algebras, and we can make some kind of a Tyazinger theorem for them to calculate the indexes and so on. That is why I am interested in that. But what that means? That if you have got a symbol, here you're multiplying on some value, and here you must have a derivation. So very important question: what is the what derivation? Where you must find the derivation to calculate something. So that is why I was interested about derivations, and why I was interested not just to understand whether there are derivations or no, but I was very interested to understand formulas for the derivations. And so that is what I'm going to talk about.
I think that you can take log of D is an example where you take the commutator.
Let's just talk about further differential operators and the end of the talk. It's a big and interesting discussion. Not now. Now we will just calculate derivations. I just want to say that there are some reasons to research this. And I know some of such reasons. And I have got my personal motivation to research it. So the main method of this research is, I call it a character method. It was promoted in joint work of me with Professor Mishchenko and Professor Stern, I'm sorry. I believe I write correctly. And it was promoted in the paper of year, I think, 16. But results which I'm going to talk about today, they were published in my personal papers. But the message was first presented in this paper. Александр Сергеевич. Ну, допустим, ну, возможно, это было мое дурное влияние. Я его в алгебре понесло со мной. So, it's a lot of nice things. Now, not such nice. We have to calculate something and to understand what we're going to talk about more procedurally. So, right now, I will talk about derivations. I will not be interested about boundness. We will return to boundness a little bit later. Now, it's important for us to understand if the operator, if you have got an operator, the derivation, which is linear and holds Leibniz rule, what does that mean? Of course, you can take two basis elements from a group. They are basis for a group ring. Group ring is a vector space with such basis, of course. So you can multiply. Well, first we will write another formula. What is the on G? It's a linear operator, so you can write it in the following way. Sure, if we are talking about group algebra, this sum is finite. If we will, when we will return to bimodules, this sum is not finite, but it's just a formula for linear operator. If you write, what is this? Of course, this is something like that. Sure, but also because the Leibniz rule holds, it's the following. And you can rewrite it again. So what you will have, we will get the following, something the plus some G1 sum the something too much sums. G1 sum, sure. Yes, thank you. So, and this is equal to this. That means that if you fix here an element h, you have got some condition on this coefficient and coefficients of this. It's not very difficult, and also it's not interesting calculation. So I just will write an answer. That the following condition looks like that. G1, because I'm sorry. I'm sorry.
They're up, down, and they're down, up.
H
Anyway, it's something like that.
H should be.
It's not a big deal.
Yes, it should be, but well, I will write in another way. I'm sorry. Yes, from that formula it must be. But anyway, what's important in this formula? That you have got some complex number here, you sum them, and you have got another complex number. So this is true for all h. It's a natural idea to say that this is written on one arrow, this is written on another arrow, sorry, and this is written on the composition. So I say that they're a groupoid of adjoint action, and these coefficients are a check of that groupoid. So I'm sorry, but I need to give you a construction of that groupoid. We will reach. So I will write here. I will define. I will tell. I believe that specialists on category theory are not here. But if they are, I say that my categories are small, so objects are sets. So I will tell a set, yes, but perhaps if somebody will listen, they will write about me to my university that I don't understand what is category. No, I understand what is a category, but I'm talking about small categories. Groupoid gamma, it's what? It's a pair of objects and arrows or morphisms. So objects from the groupoid are just elements of group. And arrows are pairs of group elements. Very interesting, but not. But I must explain it. Sorry.
G1 type, G2.
No. Just we have got one. We have got one fixed group. So if you have got two objects, and between them you have an arrow, then an arrow of two marked by two elements where are elements of a group. So this object is of this form and this object of this form. That's first. Secondary, if you have got two arrows, for example, here U1 over 1, here U2 over 2, and it's important that target of this arrow is equal to the source of this arrow. So where each ends, this arrow is begins. Then on about these two arrows, we have got a composition, which is given by a formula. Where 2, 1, where 2, where 1. why such strange formula? First of all, you see, I don't have here U2. Why? Because I can find this U2 from that the target of this arrow is equal to the beginning of this arrow. So you must say that the condition of composability is the following, that U1, the one inverse, is equal to the 2 inverse U2. So this is a composition, and this condition was called to have a composition. So we can find all letters. Now, why I say that this gamma is a groupoid? Because if you have got an arrow and another arrow and the third arrow, then the composition is associative. So if you take a composition this, and then with this, it's the similar when you take composition of this, and then with this. So associatively, it's first. Then you have got a natural arrow. What is the natural arrow? It's a loop. So it's an arrow which ends where it begins. Such an arrow, that composition of each with any such arrow is this arrow. I can say that this are arrows of the form A. Yeah, is the natural element from the ground.
Verify what is the identity of this between
Here it is. A, yeah. Each has the beginning in this is object A. This by this formula, it has the beginning in it. No, it's from A to A.
From A to A.
Yes, from A to A. And it's easy to see by this formula that if you have a composition of each with such morphism, you will have got the same morphism. And if you have take a composition with such morphism again, so you can just it's easy to see that it turns from this composition formula. So this is the groupoid. And why it's a groupoid, not just a category? Because for each morphism between two objects, you have an inverse morphism which goes back, such that their composition is a natural morphism. That means the groupoid. So associatively and natural morphism means that it is a category, and because of all morphisms are invertible, so it's a groupoid. In more easy words, what is a groupoid in our terms? It's the set of points, it's the set of arrows with the natural composition of them, such that you have got a natural loop around each object first, and for each morphism you have got an inverse morphism, such that the composition is a natural loop. So that means that is the groupoid. That's first. Secondary, we will return to derivations in 2 minutes. If you have got a groupoid, then you can take characters. It's a linear space. What? You just write on each arrow a number. For example, here I will write alpha, here I will write beta. Then on the composition, you must have alpha plus beta. It's the definition of the character. So the character is such a complex valued function from morphisms to complex numbers that this diagram holds for each pair of composable morphisms. So the theorem, first theorem. For all derivation, for any derivation of a group algebra exists and each single character here such that such the following formula holds. I try to list letters while it. Мне нужен склерозник. Sum HG here of HG dash. So the formula. He is a character. So what we have got here? You
take a morphism, yes? The
I-
character is related to a morphism, yes?
yes, this is a morphism.
Yes, but I don't understand. You take your category, yes, gamma.
Yes,
You define characters.
yes.
Then you explain again. What do you take a morphism from your category?
What is the character? Let's just write more prestigious definition. Character is a map from morphisms to complex numbers such that for all phi psi that they are composable holds the following: here of their composition is equal to here of psi plus here of phi. Logarithmic rule. This is what I wrote here, but sure, it's more prestigious. So what is written here? Here's the derivation. Okay, this is a sum by all morphisms which look like this. So you have to, the morphisms are pairs of two. On each arrow, you have got pair of two group elements. For any pair of elements, there is a unique morphism. So here I say that you must check all morphisms which look like this. So if here is G, then the second element here is also G. And the first element can be any. You must take all of such morphisms. You must check the number which is written on that morphism, the character, and then you must sum it.
So this in particular means that if you take a derivation, arbitrary derivation of your element G, then
then you can calculate it by some character.
but this means that G and H are always related by a morphism.
No. Well, first of all, I'm summing here by H. And this is all morphisms, which well, just a moment. I will draw one more picture to sorry.
So H is
You have got a morphism which looks like this.
Is one of these five upside.
Sorry?
The argument of key
Argument of here
is this.
is a morphism.
Oh, here it's a pair.
And pair is a morphism.
Why this pair is important?
Because I have defined it morphisms as pairs of elements. Each morphism is a pair of two group elements. Why? Which one? I check a pair UV, it's a morphism from this element to this element.
So if you can compose them, because this formula here is P composed with C. So if you can compose them, then they satisfy.
Yes, of course.
And so back to what you said, you cannot sum over all H. You only sum over the H which are related to G.
No, H, I assume here by all H. So you have got to take all morphisms of some special view. What view? This view. The second element is fixed G on which you are calculating. And first element, all elements. So what they connect? They connect element this and this, as it was written in definition.
Yeah.
So why it's magic, perhaps? Well, in fact, because of this formula. You see here, this is a source of the morphism, and this is the end of our morphism. This is why this is why we have talked on these elements. So the proof of this theorem, just calculate. Then nothing interesting. You just see that this condition of composability it gives you this rule. That's it. So examples, because it's very interesting, but these formulas are not clear without examples. If you take my favorite inner derivation, let's take A from G, basis element. So it looks like that, x to ax minus xa. The character looks like following. You must take an element A. You must take all arrows which go from A. Write on all of them 1. On all arrows which go back, you write -1. And on other morphisms, you write 0. Of course, if you have got A, here 1, here 0, then here is -1. Everything is correct. This is a character, what I say. And if you will take this character and put it in that formula, you will see that you have got just a commutator. Perhaps mine's commutator, I'm not sure about my arithmetics. But you see why? Because it's written that for each x is 1 plus 1, 1 minus 1. And for this character, on each line, you have got 1 plus 1, 1 minus 1. It looks logically. First example. So we can have got very important dilemma from this. If there is an inner derivation, then the corresponding character is trivial on loops.
By the way, you can also use backsides of the blackboard.
Okay, thank you. I'll try. It's clear why, because any inner derivation is a sum of such characters. Loop is a arrow which starts and begins in 1 point. Yes, and the morphism in more scientific way to say, but it's loop, it's more geometric term. So why this lemma holds? Oh, because for basic inner derivation, here on all loops it's 0. When you sum such characters, of course you sum them on morphisms, so their rules is always 0. And inverse is not true. There exists such derivations in group algebras that the corresponding character is trivial on loop, and the derivation is not inner. As I have written here 20 minutes ago. But well, I'll write an I'll fix an important definition. Derivation is quasi-inner if the corresponding character is trivial on loops. So by lemma, all inner derivations are quasi-inner. not all quasi-inner derivations are inner. Right now, just believe me, a little bit later, I can give an example to explain why this can happen. Important condition, quasi-inner derivations are ideal in the space of all derivations for group algebras. Because if we will return to Banach bimodules, so then derivations are not an algebra, there are some problems, but derivations in grouping, they contain the algebra, and quasi-inner derivations is a middle there. Very nice. So you can think about quasi-outer derivations. It's a factor of all derivations by quasi-inner derivations.
Phi D is this unique character that satisfies
Не понял первое слово.
using notation Hidi.
Yes, I'm sorry. This is I call this Turkic corresponding to D. It exists. It's easy to see that it is, of course, unique. And of course, it's easy to see that not all characters give you a derivation, because you can have got here an infinite sum and some not from the corresponding space and so on. But for derivation, you have got a character. So I say that there are quasi-outer derivations. It's derivations which are not trivial on loops. Is there an example of them? Yes. Very easy, I believe. Example. I think I can. We don't need it anymore. Well, we have got cyclic groups here. So example, I call them central derivations. No, not that. Central derivations. So let's take now it's a homomorphism to additive group of complex numbers. No, so tau of AB is tau of A plus tau of B. Let's take that a central element. It's an element which commutes with all elements of group. For example, here, identity element of the group. And it's right. Tau of J, Z. I say that this is a derivation. Why? Well, it's easy to see. I like this calculation. It's very easy. By formula. Tau of U V Z plus U tau at V Z. I had to write tau at V here, but it's a number, so I can write it where I want. So this is the tau Z of U, and this is the tau Z of V. So Leibniz shall hold. It's very easy to see. But it's not a very easy question whether without this category machinery. It's not easy question why it is not inner. Without characters, I don't know how to prove it. And with characters, it's very easy. So we just have to find the character. So I'm saying that my method is very good. So why? You must check. Sorry? I'm sorry? Yes. Yes. Sure.
So you associate to any derivation its character. Yes, by this theory.
Yes.
And if you take two derivations and you know
their commutator, you can calculate the formula for the character of their commutators. It looks like, не помню, по-английски свертка. Yes, I think a convolution-like formula. I'm not sure that I can write it without mistakes, but but it's not a difficult exercise. So proof, it's not an inner derivation. Why? Because the corresponding character looks like following. You have got here an element z. You have got here loops of view. I have to remember loops of such view z, z, z. And you write on this loop, it's a loop, because if you take z inversed, multiply it on the left, you get one moment. No, сейчас, господи, опять запутался. Нет, все правильно. I'm sorry, it's correct. So on such a loop, you must write tau option. So if tau is not trivial, then it's not trivial on loop, so it's not an inner derivation. So this is all proof. If it's inner, then it's the corresponding that one character must be trivial on loops, but it's not trivial on loops. So the question to that very good mathematicians, Johnson and others, I have found non-inner derivation. What's the problem? The problem that it is much bounded in bimodules. And again, what we're going to prove? We're going to prove that these derivations are not bounded and might be bounded just quasi-inner derivation. So we have defined quasi-inner derivations as derivations which are trivial on loops. And I say that, so I prove not the Johnson problem. I don't ask on the Johnson's question. I don't say that all derivations are inner. I say that that all derivations look like inner. And now, before the proof of the theorem, I want to say one more thing about quasi-inner derivations. Because this character is trivial on loops, you can write it in the following way: some coefficients of theta a here a sum by all elements of group. This is a formal sum, because perhaps it's not you cannot summarize it in your bimodule. But it is a sum of inner derivations. This is the character which corresponds to inner derivation, classical. And central derivation cannot be written in such way. Here, this is D, yes. This is this character. So from D depends this.
Chi dA.
This he A. It's this he A. They are canonical.
Key which is generated by dA.
Yes, and depends on D this coefficient. Perhaps I have to write.
That you're told us that if I give you a derivation, you will it's a key.
If it depends on D, sure.
What I'm saying is that what you are putting key A is the same as key of dA, of the derivation dA.
Yes.
That's just a little. I mean, when you write here, you mean key dA.
Yes. I say I'm sorry. I'm working about this for several years, so not all notions are good. I'm sorry. So we can return to the theorem. First, the proof is very easy, in fact. So how it looks like? We will check group algebra. We take supremum norma, and we take the closure. So what that means? That which elements we have here? Sum of x of g sum by all g from g. This is, of course, an infinite sum. And this is a supremum norma. So the function x must be bounded. You take all such sums. Now, if you have got a derivation there from C to this, I will call it A sub, from C to A supremum, then what? It must be bounded. So that means then when you take the formula, all of these coefficients must be bounded. But if D is not quasi-inner, then the corresponding header is not trivial for some loop. Of course, because if it is trivial on all loops, then it's quasi-inner. If it's not quasi-inner, that it's not trivial on some loop. So I take the loop, it's written here something, then what, any letter S. It's not 0. I check this loop, I check, and then I do the following. I check the composition of this loop with itself again and again. So we have, if I take the power k, then I have got sk. So if this derivation is not trivial on loops, then the function coefficient function is unbounded, because you take a loop, you just compose it with itself, and that's it. You can find as big number as you want. And the following, and the similar is the theorem in much more general view. If you take a norma, I'm not sure that it's correct term, but which is subordinated to the supremum norma. So what that means? That if something is bounded under this norm, then it's bounded under this norma. But the same theorem, all derivations in such closure, when I write here a norma subordinated to supremum norma, any derivation is bounded. Bounded derivation must be quasi-inner. That's it. So I proved the theorem which I have formulated at the beginning, because of course NP is subordinated to supremum norma. If the derivation from a group ring here is not trivial on some loop, then it's unbounded. It's unbounded even in supremum norma, not in LP norma. It's even in supremum norma unbounded. So that's it. What's the problem? Why I'm not famous mathematician yet? Because I cannot prove that quasi-inner is equal to inner for LP group algebras. There are some problems. I don't know whether quasi-inner and inner coincide or no. I don't know that. I think that they coincide. So in fact, I think that for LP group algebras, all derivations, not just quasi-inner, they also inner, in fact. But I don't know how to prove it yet. We are working about it. Well, perhaps you are interested whether derivations can you find such a norma that our central derivations will be bounded in such norma? Yes, you can. And it gives us a very nice, up to my think, connection with Grigorchuk's method about growth functions of groups and so on. So I will just formulate. So if you take a norma like that, some model such, and here the weight function module G, it's a length of element in the group. Well, our group is finitely generated, so you have got some length of elements, so on. This is a weight norma. And in such a norma theorem that exists such alpha that all central derivations are bounded. You can find such alpha for your group algebra. And why Grigorchuk, why polynomial growth is interesting, because if the group has a polynomial growth, then you can write here, sorry? Omega, I'm sorry. Last element of your algebra. If group is of polynomial growth, then you can write here not such I don't know how to say, not so row function. You can just write here something like polynomial in -1 degree. That's another interesting thing. I just want to say that how to prove that. Again, you must find you must look at this character, and you must understand which characters you must take to how to find such characters that you can write this formula from the right side to the left side. So you take character of which is bounded in some kind of norm in the character space, and then it will give you a derivation. So finding these characters is also connected with working with characters, with groups, and so on. What other? I said that I know that I will try to explain you why even for group algebras, quasi-inner can be not inner. What's with the time? I have time. So I will, it's a very interesting and a little bit strange story, you see. First of all, we have to return to our group weight. How it looks like geometrically. If you have got two elements, A and B, objects, such that exist, that they are conjugated, then that means that there exists a morphism of the following view. Here you must write something to make it the beginning in the letter A. What that means? That what I said in the beginning, that this is a group weight of a joint action. This is why. because each gives you an arrow between two conjugated in a group elements. That's the first idea. The second idea, to understand how the group points on this group point looks like, you need to look on this to the character on some graph. What graph? We have got, as you remember, we have got a finitely generated group. So if you take a graph, if you know what is the Cayley graph, it's very good to remember it. It's like a Cayley graph. So between two elements, A and B, you have got an arrow labeled by T. That means that A and B are conjugated by element T, by element T. So this is the graph. You just write that graphs when element between elements are conjugated, but not by all elements as it was in the group point, but just by generators. So how this graph looks like for a Heisenberg group? What is the Heisenberg group? Perhaps some students will look this lecture. They cannot remember what is it, so I will write that a Heisenberg group is a group of integer valued, of course, matrices. A, B, C are integer, and the multiplication is the multiplication. And if you will take not central element, for example, this one, then this graph will look in the following way. For some good generators, but you must not care about it. That's first of all. So I know how looks that graph. Then you can understand that if you have got a character on this graph, then you have got a character on the group point. It's second idea. And the third idea is the following. If you have got a character which is trivial on loops, then you can give it by potential. Then exists a function pair from objects to complex numbers, such that here of the morphism is equal.
Continue to speak about Heisenberg group, or it's a general?
No, it's general. It's general. That character on the morphism is equal to pair of the target minus pair on the source. What that means in easy words? That means the following. If I have got here in this morphism, here is written alpha, here morphism is written here beta, then I fix an object. I write here, for example, 0. Then I write here what? Alpha. Here I write alpha plus beta. Then on this morphism, you have got alpha plus beta minus alpha beta. Here you have got alpha. What is now on the target minus what on the source? Potential, like in physics. So for each trivial on loops character exists such a potential. So
T of phi and S of phi.
T of phi target. I'm sorry.
Source and target.
Yes, phi, where we're going, S is where we're beginning. This is the second idea. We have got a potential. And now I want to take potential of the following way. here I write 1 on all objects from this to the right, and 0 on these objects. If you take phi of phi, what you have? You have got 1. Or, no, here you have got 1, because the 1 on the right side, 0 on the left side. And you have got just finite number of such morphisms that on the right side and the left side, the potential is different. I will write it. There are just finite number of morphisms phi of the following view S G for each G, that phi of phi is not 0. But if you take this G very big, then you have got a lot of finite, but a lot of such morphisms. It cannot be for inner derivation, because how it looks for inner derivation? For inner derivation, there's just a finite number of non-trivial elements where the potential is defined. It's not clear, yes? The last idea. Another way, if the A is an inner derivation, it's commutator of A and X. Then potential looks like the following. You take A is a sum of A eta, where A eta is from a group, from the basis elements. You take here A1, A2, A3, and so on, AN. You write on them 1. On other elements, you write 0. So, if the derivation given by the character is inner in a group algebra, then the support of potential is also finite. And this is an example of a potential which has an infinite support. If you mind some constant from all elements, you will not, you will have always an infinite support for the character. But this character gives us, by this formula, a derivation from a group algebra to group algebra. It's for each G, this sum is finite. But this sum is finite for each G if you take such a character. But it's not inner, because this gives, because the element with which you must take a commutator, thank you, I'm sorry, it is given by this A1, A2, and so on. It's infinite sum of such elements. It's not an element from a group algebra. So this is an example. And I will just just formulate, because it's, well, the problem of this research is that we have got to work with different mathematics all the time. So now again, another mathematics, it's a graph theory and combinatorial group theory. For that graph, of course, I have got for such a graph where it's labeled T, which the elements are conjugated, that the dimension of quasi-inner derivations by inner derivations on компоненты связности, я забыл, как по-английски. I'm sorry. Connection error. So thank you.
Q in mod in mod there.
Of course. This dimension is equal to the number of ends of the corresponding graph minus 1. This is not a very easy theorem, but I think it's rather beautiful to formulate it.
So we take this quotient algebra and what is
Here, where? Correctly tried in the following way. That means that you take part of your groupoid which is connected with this element u. So it's for each u, you take the part of groupoid which is connected
If
with
it's
u.
some u?
Yes.
Yes.
Then you have got an area of connectedness
Connected by means of these graphs, yes?
in graphs or in groupoid, doesn't matter.
Okay.
Then you take just those characters which are supported on that area. And for them, the dimension of this quotient is equal to this, which is the one we understand, and what is the number, sorry? This ends, number of ends, I will define it. The number of ends of this graph. What is the number of ends of the graph? I say it's again another mathematics. I'm very full, sorry, but what it means? If you have got such a graph, then you have got 3 ends, because if you cut off a finite part of the graph, you have got 3, not more, 3 infinite connection areas. So the number of ends is the maximal number of infinite connected areas when you're cutting off a finite graph. So here, 2 ends, this, and this. For example, here are how many ends? You cut off this as 1, 2, 3, 4, 5 ends. So this is the
You
graph.
got u.
No, I can cut off any finite subgraph. I can watch here. Don't care, thank you. Number of ends of the graph. What does that mean? That means the following. If the gamma with the graph, then here of gamma is maximum of infinite connected areas in the graph of gamma without, let's say, gamma 0, maximum gamma 0 are finite. So that means what? If you have got a graph, you cut out any finite subgraph, and you calculate the number of infinite parts. Just infinite parts you are interested in. So maximum.
So if your graph is finite, then
It's 0.
0.
Yes. If it's a line, when you cut out a finite part, you have got 2 rows, one and another. So number of ends of a line is 2.
Let's take a very simple graph like this one.
Yes,
Yes. So what is E of
2. Of course, if I cut out finite part, you have got the infinite part and the infinite part. Nothing else.
And let's come back to the formula.
Maximum by all maximum. Well, if you
May it happen that the E of gamma is infinite?
sure,
It may be.
yes. For example, for a free group, no problems. Of course. If you take a Kelly graph, here, not this conjugated diagram, then there is a Hopf theorem that number of ends is 0, 1, 2, or infinity. I don't know how to prove it for such graphs, but I think that it's the same. 0, 1, 2, and infinity. I have got examples, 0, 1, 2, 2, infinity, and I have some ideas why it cannot be, why you cannot find the graph with 3 ends. But anyway, we don't care about it. Because what I write here, that if you take such a component, then you can calculate this dimension. Of course, if you, for a Heisenberg law, the dimension of this quotient for all the quasi-inner derivations by all inner derivations is infinite, because you have got infinite numbers of such lines. On each line, you have got dimension 1, and you have got an infinite of ones. But on the but if perhaps you have got a group which has got just finite number of conjugated classes, there are such groups. It's a theorem of Poisson. He proves that you have got some such groups. Don't matter. For them, you have got that this dimension will be finite. Perhaps it will be 0, but well, in fact, it's a very good question. I give you an example that it's not 0, but in fact, usually it's 0, because usually if you take good group, then it's the number of ends of such a graph is 1. In fact, it's infinite, and it's 1. But you have got examples. It's as it's usually in group theory. You have got bad counterexamples for almost all theorems. That's it. I think I will finish right here, because потому что меня, по-моему, уже невозможно слушать.
Thanks a lot. Questions, remarks, comments? No, then thank you very much again. And so we meet in 2 weeks. The next session will be skipped by private reasons. Goodbye. Thank you.
Thank you for the invitation.